Today I'm going to talk to you about chemical identifiers, the capabilities, connections and contradictions that you will find when you're using complex chemical identifiers to map between different sources of data, databases, applications, and those places that we use commonly in our day-to-day world of doing scientific research. I'm going to give you an overview of the various flavors of these identifiers, strengths and weaknesses, how they can be used to form connections, but where you'll still face some significant contradictions. And I'll talk about the great progress that's been made, but we still have a lot of challenges ahead. So if you're sourcing data from online data sources, where do you start? I've shown a number of logos right here, PubChem, eChemPortal, ChemSpider, for example. But when you take data from these sources, what do you trust? How do you verify? If you're going to make decisions based on these data, you have to move through the process of trust but verify, and it can be slow and exacting. I've published on this a number of times, and if you want a lot of the details, please consult a couple of these publications. We've been working on chemistry curation a long time at the EPA, and one of the outcomes of this work has been the DSS Tox database. It's over 2 decades of curation work, and while ChemSpider, PubChem, and SciFinder have over 100 million chemicals, we're only just about 1.2 million, and that's after 20 years of work. However, we are providing access to the public via the Comtox Chemicals dashboard, and here you will get the benefit of all of our curation work where we are dealing with some of the challenges around chemical identifiers. I'll be using this application and the underlying database for some of the examples I highlight. Many of you are using registry numbers, either CAS registry numbers or some of the European-based EC numbers, INEX numbers, etc. You're all taking benefits from systematic names, UPAC names, CAS names. These are rules-based so that they can be converted back to structures. The in-sheet chemical identifiers, of course, have brought great benefit to the internet in terms of linking. We've got common names and synonyms, pesticide names, drug names, etc. All the database identifiers, KEBI, PubChem, ChemSpider, and hundreds of other identifiers because of all of the databases available for chemistry today. Also, you've got the chemical structures that can be represented in text format, SMILES, WISWESA, for example, and of course the formats for data interchange of chemicals. This is easiest seen here in this screenshot showing parts of the Wikipedia DDT page where you have the chemical structure right here, the INSHI, both standardized and non-standardized INSHI. You have the SMILE string. This is a systematic name, which I will show the benefits of this systematic name for conversion, as well as all of these identifiers which link out to other resources. Systematic names can be converted back to the structure on a site such as Opsin, and notice when you do this it comes back with an INSHI key and SMILES also. INSHIs and SMILES, they can be converted back to the structure, but only for the string. The INSHI key is actually a hash, and that is a lookup, which I will talk about a little more later. CAS registry numbers, incredibly powerful in commerce, and CAS has done a great job at making these available of late for a very limited subset of the hundreds of millions of chemicals that they have. We have 500,000 chemicals now available on Common Chemistry. This was released in 2021. There is a publication detailing this, and if you search here for the CAS number, you will find the structure, lots of details such as other names and identifiers. We gratefully thank CAS for doing this work for us. INSHI keys have made the web structure searchable, so here's an example of where I've taken the standard INSHI key for DDT. I've searched it online, and we can find links into the mass spec database, into PubChem, and into Google Patents. Google have done a lot of work with their Google Scholar, Google Books, and Google Patents to use INSHI keys and lay on structures to make their entire resources structure searchable. And the European Bioinformatics Institute, EBI, has built Unichem, and they've done the work of mapping together many databases. We're also very grateful for the work they've done there, so that in this case, if I come to their compound search, paste in an INSHI key that has been generated on any of the other websites, this will allow you to link out to almost 40 different databases just by using the INSHI key. So it's greatly beneficial where you want to find for an INSHI key from any database, whether it's available in Chembl, whether it's available in zinc, e-molecules, etc., etc. These are all linked up directly into the databases. So Inchi keys are very enabling. And the challenge we have with other identifiers, and many are simply lookups, just like the Inchi key. Think about trade names and synonyms. These are simple descriptors of a chemical, DDT, dichlorophenyl trichloroethane. These are simple names or abbreviations that you can search on, but they're not systematic. They cannot be converted. They have to be looked up. Database IDs are the same. If you get a ChemSpider ID, you have to go to ChemSpider to resolve it. There are many resolvers that are coming online, and these are greatly beneficial to us. Many of these deliver web services so that those of us who are building chemical applications can use these web services for integration. CABI is an excellent example. Again, this is from EBI, European Bioinformatics Institute, and the National Cancer Institute, NCI, have built up their identifier mapping service. This has been online. The chemical identifier resolver has been online for years and is used by tens of thousands of people at this point. And you can convert between different identifiers. If you're not aware of this, I recommend you check it out. The FDA have got unis. These are their own identifiers, and they have a lot of challenges that a number of us are glad that they deal with and we get the benefits from. And that is dealing with the complexity of generating identifiers for botanicals, complex mixtures, etc., etc. So the uni system that FDA has made available is mapped via the example I gave you from EBI for Unichem. However, don't forget, many chemicals don't have chemical structures, so there will be no Inchi key mappings to resolve in that case. There could be very significant contradictions in identifiers, even at the most simple level. So think about it. What is hydrogen? Do we mean the element or the gas? H or H2? Are we thinking about hydrogen as a liquid, a solid, or as a gas? At what temperature, at what pressure? So identifiers will get you so far, but annotation, a description of what you mean, generally has to be layered on. Think about that in a little more detail when you consider carbon. So carbon is available in very many forms. It's allotropic forms, graphite, diamond. We have buckyballs, graphene. These are all carbon for sure. And how complex can this get when each has its own CAS number, its own name, its own description? So if we look here on PubChem for carbon, this is the carbon substance page. You can see here a number of CAS numbers listed from a number of sources. Here's a number of those CAS numbers listed here. And when we resolve these on our own system, we find that they are actually segregated out. So diamond has its own CAS number and substance identifier, as does graphite, charcoal, nanotubes, etc., etc. Carbon is, in theory, a simple example, but has so much complexity. If you now look at the number of deleted CAS numbers on PubChem, so this is the PubChem page showing deprecated CAS numbers for certain substance-related relationships for carbon. Here we're looking on SciFinder. You can see that even though there may be one active CAS number for a substance, there's so many deleted CAS numbers. Some of the chemicals we deal with have hundreds of deleted CAS numbers. CAS are powerful in terms of the value of those identifiers, but can get misused and mapped problematically. In this case, showing on Cameo chemicals, we see that the CAS number for zirconium is displayed for 6 separate substances. This is zirconium suspended in a flammable liquid. This is dry zirconium powder. This is wet powder. This is scrap. They're all zirconium. They all have the same CAS number, but they have different properties and safety. Identifiers can be challenging and will only get you part way. Here's an example more in the world of today where we're looking at PFAS chemicals. Many people think of PFOS and PFOA, two of the primary PFAS chemicals of discussion nowadays. Perfluorooctane sulfonic acid, perfluorooctanoic acid. Structural representations are shown here. The linear forms would be acceptable to most people. The CAS numbers would map to those linear forms. But just think about it for a moment. Perfluoro, everything is fluorinated. Octane, 8 carbons in a chain. Sulfonic acid and octanoic acid, so those are substituents on a C8 fully fluorinated chain. That's what that describes. So does that mean the linear form? Not necessarily. If you look at PFOA, perfluorooctanoic acid, there are actually many linear and branched forms that you can draw. And these are those examples here. However, some of those can have stereocenters also. So you actually have the R form and the S form to display. So P4 is not as simple as one linear form. It can be linear and branched. It can be a mixture. It can get very challenging. This gets even more problematic when you think of categories. For example, polychlorinated biphenyls. There are 209 of them in the set, and this is a structural representation of that set with its own Cas number. But this is a class of chemicals. This is a side chain where you can have X and Y can vary in length. This is a complex alkyl linear benzene sulfonate. This is dieldrin, where stereochemistry can vary at each one of those stereocenters. So these each have their own Cas numbers, they each have their own names or synonyms, but exchange is hard at a structure level because structure representation is incredibly difficult. Many other identifiers are ambiguous. There are chemicals that don't have defined stoichiometry of 1:2 ratio, for example. So here we see examples where it's 1:X. X is undefined. What about PFAS chemical identifiers that are being used now in the public domain in presentations and publications? These are very ambiguous in definition and extremely difficult to map all of these back to clear, clarified chemical structures. It gets even harder when you don't have explicit chemicals. Here we have a list of Cas numbers. They look very related just in terms of serialization. Here you can see the descriptions. These are complex substances. They can be polymers or mixtures or reaction products. There is no way to represent these as chemical structures. We can't get INCHI keys. Very difficult to map these together. Our own experience with identifiers is that we had to add our own, the DTX SID. This is the DSS tox substance identifier as we built our own database. In our application, we are integrating Cas, both active and deleted, all of the synonyms we can, systematic names, smiles, etc., etc. Everything I've discussed gets mapped to our substance identifier. And this is accepted by Wikidata. It shows up all over Wikipedia now. But identifiers are generally not enough, as I said. You have to use some type of annotation. So we add QC notes to the chemicals that we register, and we integrate to other context. By doing this in one application, where we are pulling it all into one systematic approach to integrating identifiers, we can then build a link farm, and this is an example page for DDT, where we are linking across over 90 different websites by using mappings of Cas numbers, names, INCHI keys, smiles, to link from our capabilities in our application out across the internet. This would not be possible were it not for the power of chemical identifiers, the various flavors, and what can be done with them. But there still can be so many contradictions. What I've been trying to show is that chemical identifiers are enabling. There are many flavors, they are difficult to deal with, they are complex to manage and integrate, but we can make great progress. The examples I've shown are around organic chemical structures, explicit, well-defined. I use DDT as an example. PFAS is more ambiguous. But then we have the challenges of inorganics, organometallics, polymers. There's not as much progress made here yet with the INCHI, but it's coming. People have been working on supporting these types of chemicals through INCHI for a while. We will see more progress in the near future. There is also the MINCHI, that's the mixture INCHI that is in development. So chemicals without structures are harder to cross-link, but Cas numbers are very enabling, but you've seen the challenges there also. The FDA uni identifiers are beneficial, but also takes a lot of work to map between applications. I remain with the position that human annotation and curation is going to be necessary for the foreseeable future. Our own contributions in this area of chemical data curation, complex substance representation, and data exchange, we believe have improved the situation. We have way much more to do than we can deal with at the moment, but we eat into this every single day we can with our curation team. I do point you to the work that we did recently on mapping together 20,000 Wikipedia substance pages. This has been a work of passion for a number of years to make sure that we can use the snippets from the Wikipedia pages directly into our application. I hope this was useful for you to understand the challenges that we have ahead and the capabilities that already exist for chemical identifiers. Thank you.